Thank you. So I'm going to talk about async today. How many of you have played around with async already? Okay, so I'm preaching to the choir, basically. That's good. Let's get started. So who am I? I'm Marc Lemburg. I've been with Python for a very, very long time. You probably can see that I'm very old. I have a company, a consulting company. We're doing Python projects and building things for clients. And because Python is so productive, this makes a lot of sense for both us and the clients. I'm also working as a consulting CTO. So if you have a startup, you need a CTO, then come talk to me. As Daniela already said, I'm very active in the Python community. So I was chair of the EuroPython Society for a number of years. Also on the board of the PSF, and I'm a Python core developer. If you've ever touched Unicode, then you can blame me. I'm based in Düsseldorf in Germany. Right, so before I get into this, the slides have a lot of text. I don't know if you can read it. I'm going to post the slides afterwards. I'm also not going to read all the text that's on the slides, way too much there. The purpose of those slides is really to also provide some kind of reference for you after the talk, so you can have a look at that. So what's the motivation for the talk? So the motivation is that we have a Python user group in Düsseldorf called the Python Meeting Düsseldorf, and we're using Telegram for managing the communication with everyone in that group. And about early last year, we started seeing some strange signups to that Telegram group. There were lots of signups coming in from people who obviously didn't really want to talk about Python, but instead they wanted to talk about cryptocurrencies and how to rip us off in strange ways. So we had to do something about it. At first we just manually basically just banned them every now and then. We just had it maybe like 1 or 2 per week that we had to handle. But in recent months, it's actually become a real pain. So we typically get 5 to 10 such signups every single night. And so we had to do something about it. I sat down and then wrote this bot, and I used a library for that called Pyrogram. How many of you know that one? No one. You should definitely have a look at that if you want to write a bot for Telegram. It's a very nice library. It's well maintained. It's a bit new, but the person behind it is really doing a great job there. It's fully asynchronous, and that basically enters the topic of the talk. So what's this asynchronous programming anyway? Now, many of you already know, so basically preaching to the choir, but for those who don't know, I'm going to cover this in a bit more detail. So there are essentially 3 execution modules that you have in Python. One is synchronous, the other one is threaded, and then you have asynchronous. And asynchronous is rather new in Python. So synchronous, very easy. You do everything step by step. Every single step has to wait for the next step for the previous step to complete in order to start. Which is, it's easy to do. You don't have to think about a lot about synchronization or sharing resources. But of course, waiting is not really a very good strategy of how to use the resources. So you want to do something about it, especially because you have multiple cores in your CPUs. So you then look at threading. So threading is basically something that is provided by the OS. It's not provided by Python itself. It's also managed by the OS. And that causes a number of issues. I won't get too much into those issues, but one of the biggest issues is that you actually have to protect your resources that you're using in your application against concurrent use. So you can have, let's say, a dictionary being manipulated by one thread, and at the same time by another thread, and those two can clash and then cause data corruption. Threading is, if it's done in C, it's very efficient. It's a very good way to handle concurrency, and things actually run in parallel. So if you have multiple cores, all the cores can actually be used. Then we have asynchronous processing. So asynchronous processing is actually very close to synchronous processing, except that every now and then you tell the application, or more specifically the event loop, that at a certain point in your application you can give up control to the calling function. And then if you design things properly with an event loop, then you can actually share the resources that you have, and you can make it so that whenever you're waiting for I/O, for example, you don't have to have the whole application wait for I/O, but just one task that's running and waiting for I/O, and then you can do something else in the meantime. So that's a very nice way to use your resources, but all the players in that game have to cooperate. So that introduces something new to your application, and you have to think about that. So why isn't everyone using threading? Well, many people are actually, like Windows, for example, is full of threads. But the problem is that we want to use Python, and Python has this concept called a GIL, which is the Global Interpreter Lock. How many of you know the GIL? I mean, not personally, but you know what it is. So the GIL was introduced into Python at a very, very early stage because Guido wanted to add threads to Python, and using a GIL is a very easy way to protect all your resources. So you basically say that the Python interpreter can only be used by a single thread at any point in time. So whenever you use threads, only one thread can actually use the virtual machine that's built into the Python interpreter. Of course, if you do I/O, you can release the GIL, and you can say, okay, I'm going to release the GIL at this point because I know that the code I'm running now is not going to call back into Python, so other parts of Python can run in other threads. So that's very much possible. So if you like reading a file, for example, or doing some long calculation, that is perfectly possible, and it's also a very valid way of operating. But of course, it's not ideal, and we like to make it easier, and that's also why the async I/O got added to Python recently, well, a couple of years ago. So let's have a look at what threading and Python, how they work together. As you can see in this image, I have 3 cores. The 3 cores are run by a single process, and each core has a thread. You see these orange fields here. This is actually Python, the Python interpreter running. Then you have the yellow ones. This is basically code that it's not running, it's waiting. And then you have these bluish ones. Those are parts which are waiting for I/O. Now, if you look at this a bit closer and you basically move things around a bit, split them out, you can see that even though you have 3 threads, there's just one single flow of control where the Python interpreter is running. So even though you have 3 threads, you're not really making use of those 3 cores that you're using there. So you want to do this a bit better. And that's where asynchronous comes in. So it makes it possible to, instead of occupying 3 cores, you can occupy a single core and then wait on I/O by basically saying, okay, this is a task. This task is currently waiting on I/O, so I can run some other task in between. And then again, you see that you have a single line of code running in the Python virtual machine, but it's only occupying a single core. And if you want to, you can then have this single flow of execution. You can have that in multiple processes and then use all your cores more efficiently. What's important to note, though, is that there's no parallel work going on. And even though that may seem like something that's not so nice, it's actually very good because it makes writing these applications a lot easier. They look very much like synchronous code that you're writing. So let's have a closer look at how it works. In order to write these asynchronous applications, there's this concept called coroutines, which is essentially just a subroutine, except that at certain points in that subroutine, the subroutine can say, okay, I'm waiting for something, so I can give up control to the caller. And then if the caller further up is actually inside a loop, the event loop, then you can manage different tasks and you can pass on control to another task. And when that task then gives up control again, you can basically then return to the previous coroutine and continue where you left off. So that's essentially the concept behind coroutines. Python 3.5 added a few keywords to make all of this easier. Before we had yield from, but I don't think that anyone is using that anymore. Most important are the keywords async and await. Async basically tells the interpreter that this is going to be a coroutine that you're writing there, and await tells the coroutine to basically pass back control to the caller. There's this nice package called asyncio in Python, which you can use to control all this, and I'm going to go into this a little bit further later on. So let's have a look at an application, very simple application that uses async. So on the left side, you have a synchronous program. The synchronous program, it calls a function, and then it does something. I just put a sleep in here, and then it returns. Very easy. In the asynchronous example, I have a coroutine that I define. It also does something, also sleeps for a while, but if you look closer, then this sleep is actually not this regular sleep that you have in the time module, but it's a different sleep in the asyncio module. And that sleep allows you to basically return control to the caller so other tasks can run while that particular task is sleeping. And you see in the next part down here that I'm actually creating two tasks, and those tasks are running, simulatedly running in parallel. So you define two tasks, you tell Python to run those tasks using the asyncio gather call, and then it will run both tasks at the same time, and then pass the control between those two tasks. So that's essentially how it works. Let's have a close look at the asyncio module. So first of all, of course, you have management functions. So you need to tell the Python interpreter to run something as an async application. And that's typically done by using asyncio.run. That's how you basically start your main coroutine that you have in your application. Then there are some other functions like this gather function. Gather is interesting if you want to run multiple tasks more or less in parallel. And then sleep I already mentioned. This is just for giving up control at certain points. If you like, if you're waiting for something, if you want to synchronize with something else, then you can use that function. It's also possible to wait on coroutines or completion of coroutines in different ways. So there are wait for and wait, which allow you to wait for a coroutine to finish with a timeout, either for just one or maybe a set of those coroutines. Then next is the task object. The task object is basically an encapsulation of the concept of calling a coroutine. So it schedules a coroutine call. You don't really have to know how it works internally because you are not even supposed to create these objects by yourself. These objects are created using asyncio create task, and then you just pass around the object that you get. The nice thing about create task is also that it automatically schedules your call. So if you want to call something, then you can just pass it to create task. It will take the coroutine, create a task, schedule it for execution in the event loop, and then it will more or less at the next slot that's available will get executed. You can also query the number of tasks that are currently running. You can ask for the current task, you can ask for a list of all tasks, and then you can use that for introspection. Now I've been talking about this event loop a whole lot. So event loop is really a very, very easy concept. It's basically just a while loop that runs forever, or let's say at least until everything is, has been, all the tasks have been executed, and then you say, okay, I want to end my main coroutine. In that loop, the control always gets passed on to the next task objects, and then whenever a task object returns using the await, then you get to the next slice, and then you execute the next part of the next task that's currently in the queue for the event loop. Sometimes you have blocking code, so code that is not written to work in an async environment. So what do you do there? Well, one way is to just call the blocking code. which is actually a bad thing to do because it basically blocks your event loop. And if the event loop is not running, nothing else is going to run in your asynchronous application, right? So you have to be careful about these things. Sometimes you know that something is not going to return immediately or not going to give up control. In those cases, you can wrap things into threads and then have those synchronous parts, the blocking code, run in a thread. And so the other parts can continue running in the asynchronous event loop. Sometimes it's not possible, and then you just see errors in your log files, and then you have to go investigate. This part can be frustrating when you're writing these applications, especially if you're calling out to third-party libraries and you don't know what's really happening inside those libraries, whether they take more time or not. And of course, there's a lot more I cannot really cover in this talk. I just put down a couple of keywords here. If you're interested in those things, then I suggest going to the documentation and reading up on those things. There's a lot of support for the various things that you might want to do with async. For example, if you want to have sockets that work cooperatively, then you should look at the socket support that's there, also for timers, servers, and other things. Now, let's have a look at the ecosystem around async I/O. Obviously, like I said, blocking code and non-blocking code, or async code, they don't necessarily work together too well. So a lot has been done in recent years to basically create new libraries that are compatible with async I/O. In the standard library, you get the async I/O module. You can also change the event loop that's being used in Python for a faster one. There's one called UV loop. So if you have a need for like a faster event loop, then that's something to look into. If you want to work asynchronously directly with, let's say, databases or web servers, or want to do web requests or so, there's a huge collection of libraries out there called AIO libs, and there's this central GitHub repository here where you can find those things. I listed a couple of such libraries here. One thing I want to note, though, if you want to use a database module of one of these implementations, and many of these database modules, they don't support transactions anymore. And if you're doing any database programming, serious database programming, that may be a bigger issue. So it may sometimes be necessary to wrap something in a thread and then have transactions again using the blocking interfaces instead of using these interfaces. Depends a bit on what your use case is. If you go to the higher level, so what I just covered was low level. If you go to the higher level, then there are a couple of other interesting packages you should have a look at. For example, Tornado is probably well known. Starlet, probably not so well known, but it's actually being used in FastAPI. Strawberry is a very nice GraphQL server that works asynchronously. Django is getting support for asynchronous as well. I don't really know how far they are yet, but it's definitely coming. It's definitely moving in that direction. If you've been using Unicorn, for example, for whiskey kind of applications and hooking whiskey applications into your web server, then there's UVcorn, which you can use as more or less a drop-in replacement for that. And there are some other things like Quart, for example, very nice. So these are things to check out. Now, I've covered a lot of things, a lot of details, probably bored you a bit with all this async stuff. Now let's get back to the original question. So that was writing this Telegram bot. We have the Telegram bot on the website, on the GitHub account, or you can just search for eGenix and Telegram, and then you find it. I won't go too much into the details about how to write those bots. Just want to mention a couple of things that need to be considered. So one thing is that, for example, because you want to capture the complete dialogue with these people who are signing up, or bots signing up, you have to basically catch the complete conversation with them. What you typically do is you start with subclassing from the Pyrograms client, then you do standard stuff, configuration in the Python file, so we chose not to use a YAML file for this. Everything gets delivered as a Python package to make it easy to install and also to run. How many of you know this dunder main.py method? not so many. So that's a very easy way to make your package executable directly from the command line. So you can use this Python -m and then package name. And then what Python does is it goes into the package, finds this dunder main.py file and runs it. Observability is, of course, something that you need to implement in such a bot because you want to know what the bot is doing. And because I was lazy, I didn't want to go to the server all the time and look at log files. I just had a separate Telegram group set up and I sent all the log messages there, which makes it very easy for me to monitor what the bot is actually doing. Like I mentioned, we need a catch-all handler. Pyrogram actually does implement the Telegram bot commands, the / commands, but of course, spammers don't call the bot commands, so that wouldn't work. So I have to basically look at all the different messages, and that's also why I need something asynchronous, because I actually need to put all the messages that are going to the group through this bot. And whenever I/O happens, I call out to the async. I use async methods, so you have these awaits in here. I don't know if you can see any in here. It's a bit small, and I have the wrong glasses on, so I think this is better. I think there's some asyncs, some awaits in here. So essentially what you do is you write your synchronous code, and then every time you have a situation where, okay, I'm waiting for something's going to happen. Let's say I want to write a log message, or I want to write to a log file, or send back a reply to something, then I can use await. And whenever I use await, it means I can give up control, something else can happen, some other message can get processed. So the first results from running that bot. So we implemented that bot in March and April. Since April, it's been running in production. And so far, we've banned 390 spam signups, which is quite a lot because we just have about 115 members in that group. So we kind of lost a lot of members, but probably for the better. If we would have done this manually, we would probably have spent like 13 hours, maybe even more, on this administration work. So that saved us a couple of hours. If you take the development work into account, it's probably going to break even end of this year. And I would say that, well, it's working. So yeah, that was a successful async program and implementation. And so all I wanted to say is basically the main takeaway from this talk: async is great, give it a try. Thank you.
Thank you, Marc-Andre. We do have time for maybe a couple of very short questions. So do I see any hands up for questions? There's one at the back. While I'm doing that, perhaps you would answer one for me, which is, I didn't truly understand this simulated parallel work and why it's where is the advantage in that?
Yeah, let me just try to find the slide. LibreOffice has a slide selector, but let me see whether I can find it over here. Is it shown? Yeah. So with simulated, it's a bit, you can't see the cursor, right? Or can you? Yes. But I can't see it. Okay. Well, with simulated, I mean, it's not actually running in parallel because you have a single core running here, over here, right? This is your single core. And the single core, of course, can only execute one instruction at any point in time. And so what happens is it first goes to this task, and then it goes down to this task, and then executes this task. But it's really only simulating doing something in parallel. In reality, it's just executing everything, in a synchronous way. It's just that when you get to these points, the blue ones, where it waits for I/O, then it actually looks like it's doing something in parallel, because one task is waiting for I/O, while another task, in this case this one, is being run. So that's why it's simulated parallelism. It's not like with threads. In threads, you actually have multiple cores run in parallel.
Hiya. So in your Telegram bot, you've kind of gone from a top-down approach for the async stuff. Your entire use case is started with something that is very async. Do you have any advice for how you can kind of adapt existing libraries where you have both synchronous and asynchronous consumers? Or do you just have to kind of bite the bullet and wrap all of your async methods in like some synchronous caller?
No, you don't. I mean, it's basically possible to and it's also very common to wrap things that you cannot easily run asynchronously into threads, and then to expose both an async interface and a synchronous interface. FastAPI, for example, is doing that. In FastAPI, if you run or you register a function that's supposed to be exposed to the outside using FastAPI as a server, and you write that as a regular function, it becomes a synchronous function, a blocking function. If you write the same thing with async in front of it, then it becomes an asynchronous function, and then FastAPI will then handle this as an async entry point and will process everything asynchronously. So you can basically get the best of both worlds using that approach. If you have an existing library and want to convert that to handle both, unfortunately, you do have to have the main entry points as both synchronous and asynchronous entry points and methods, because otherwise Python simply won't handle these things as coroutines. And if you use a synchronous method in an asynchronous program, then it'll basically block things, so it won't go back to the event loop. It's also not possible to, if you have let's say a regular function, and then inside the regular function somewhere you try to call an asynchronous function, the asynchronous function cannot pass control back, going beyond the synchronous function that you have there, because there's no way for that function to return to the caller. I'm not sure if I'm making myself clear, but this is essentially how it works. Or doesn't work. More questions?
I think we have time, Alex, we have time for a micro question, possibly.
You mentioned early on in the talk that the asynchronous database libraries tend not to have transaction support. Is that just they're new, they haven't got it yet, they will, or is that something fundamental to async that means you can't have transactions easily?
I don't really know. It's a very good question. My hope is that eventually they will add transactions again, but I'm not really sure whether they're that interested in these transactions, because there's actually a database API for asynchronous programs. And they are focusing very much on non-transactional database access. In some cases, that's good, right? So if you have a Django, for example, and you just do CRUD kind of work, then you can basically do without the transactions. If you're, let's say, into banking and you want to do transfers between different bank accounts, and then something breaks in between, then you certainly want to roll back everything automatically, right? So that the money stays in your original account, and you can retry that operation. The problem with databases not being transactional is that it's extremely hard to correct the mess that gets created in case something goes wrong in the middle of what's supposed to be a transaction, right? Because first of all, you don't know what has actually ended up in the database, and the second thing is that sometimes you have multiple databases being used, and so it's very complicated or complex to then undo these operations.
Thank you very much, Marc-Andre, for your insights, for everything you've done in Python for us, for Python. So thanks again. We're going to a coffee break.